Okay, so now I think we can move on to section 4.3, which talks about the properties of the definite integral. And so, without getting into too many details, we do want to define what we mean by definite integral. And we sort of started that in 4.2, but not officially, right? So let's get to the definition. It is kind of a technical one, but I'll try to go through it somewhat carefully here. So we have a function f, right? So let f be a function, and it's going to be defined on a closed interval from a to b, right? And we're going to let this little triangle here, that's the Greek letter delta, right? Remember delta x? But we're not going to use, this is not delta x, it's just delta, right? So it's a partition of the interval from a to b. And I think we defined partition last time, but, so if this is the interval down here from a to b, right, a partition is just a way to divide it up. And up until now, we've been dividing this interval into equal parts, right, equal lengths, or equal widths, I should say. But in general, it doesn't have to be, right? So this might be your x1, this might be x2, this might be x3, way over here might be x4, this might be x5, and so on, right? So your a is x0, and your b would be, well, the last one, xn. In this case, it would be x6, rather. So I'm dividing this into, let's see, 1, 2, 3, 4, 5, 6 intervals, right? So it's so that's what we mean by a partition. A partition is just all these x values here, right? So from x0, x1, right, the dividing points up to x6, right? Or xn in general, right? And that has to be your b, right? So b has to be xn and a has to be x0. Yep, we're starting at 0 because, right, otherwise you'd have one less than that, right? In other words, if you started at x1, then this is 2, 3, 4, 5, 6, 7, right? Oh, wait a minute. 1, 2, 3, 4, 5, 6, 7. Yeah. So it would go to x7, but you only have 6 intervals. So that's why we start at 0. In any event, so that's what we mean by a partition. It's just a list of numbers, a list of the dividing points of your interval. Okay. And now your delta x, right? Your delta xi, because they will all be different, will just be the difference between the two x's, right? Right. So for example, what would delta x3 be? Well, it would be x3 minus x2, which would be this tiny interval in here, right? On the other hand, what would delta x4 be? It would be x4 minus x3, which would be this much longer interval, right? So your delta x's are not the same here, right? As I think I mentioned last time, they don't have to be the same. Okay, right? So we have that partition, and ci is just any point in the middle of these intervals, right? So for example, c4 could be right here. Right? C4 could be anywhere between, x3 and x4. Okay. All right. So now this sum here, this summation here, right, is referred to as a Riemann sum, right, for a given partition. A different partition will give you a different sum. In fact, a different choice of C will give you a different sum. But so it depends on the partition. It depends on what your C's are. Are they in the middle? Are they the left endpoint or the right endpoint? That will matter, right? Okay. Now we get to the following definition here. We have, right, so same setup. We have a function defined on a closed interval, and then we want to take the limit of the Riemann sums, right? So now we're taking the limit, let me write that this way, right? The limit as the norm of the partition goes to 0. I'll talk about that in a second. Oops, not the function, but the sum, right? The Riemann sum, I going from 1 to n, of f of ci delta xi, right? So what do we mean by this symbol here, right? I'm calling this the norm of the partition. definition. Right. So the norm is simply the length of the longest interval. Okay. So in this example here, what's the longest interval? Well, it looks to be this one in green here from 3 to 4. Although this is pretty close as well. That might be almost as long. And they might be the same, right? So in that case, whatever length that is, that will be the norm of the partitions. Okay, so that has to go to 0. And you might think that's the same thing as just saying n goes to infinity. Obviously, if you have more and more intervals, if you divide this up into more and more rectangles, right? More and more intervals, then, of course, as n gets bigger, the longest interval has to get shorter. But that's not necessarily true, right? You can imagine the following situation. Here's your interval, and I'm going to say that this is my x0, this is x1, and this is my xn. But I'm going to divide this up into smaller and smaller intervals here, and then here, right? While keeping this the same. So your n could go to infinity, and yet you still have this interval. That's the longest interval. That's still finite. That might not go to 0. Okay, so these are, not technically the same thing, but for our purposes, we're not going to worry about it, right? Last time we just set n going to infinity, and because all the intervals were the same, that ensured that the norm of the partition would also go to 0, right? But yeah, so there's a slight difference, but again, it's only because all our intervals don't have to be the same length. Okay, so if this limit exists, so going back to the definition, right? If this limit exists, right? So if this limit exists, then we say that f is integrable. That means we can take an integral of it. And then this symbol here is the definition of the definite integral, which I think we did last time, although, we did this less generally because we had n going to infinity, right? And so, yeah, if the limit exists, right, f is integrable. And that just means we can find the area, right? If the area exists, that means the definite integral exists, and then we're good, right? So, right, by good I mean the function is integrable, and you get a finite area, right? Yeah. So I hope that helps. Sorry to make you very dizzy there. But again, as a practical matter, we're not really going to use this in any significant way. It's just getting used to the idea of, right, what is a definite integral, right? So I'm going to define that again. Let me get rid of all this clutter here. Okay, so now we can talk about the definite integral, right? So it's this symbol here. This is the definite integral of a function f, right? And so again, what is the definition? Not something you really have to worry about, but technically it is the limit of, as the norm of the partitions go to 0, of the Riemann sum, right? I going from 1 to n of f of ci delta xi, right? And that is the definition of the definite integral. As a practical matter, what does this represent, right? What is the definite integral of the function, right? So over here on the right, you have the graph of this function here, f of x, from a to b, right? So we're going from x equals a to x equals b. It's just going to be the area, right? It's going to be this red area in here, right? So the area under the curve, right? So, well, instead of saying it that way, let's say it's the area bounded between the x-axis, right, which is just y equals 0, right? And that's the lower boundary. The upper boundary is the graph of the function, right? So the graph of f of x, right? And also between x equals a, so that's a vertical line, and x equals b. Okay, so this, in other words, this finite region in here, right? So that's the area, right? So that's represented by this this symbol here, right? So this symbol just represents area, right? So that's the big takeaway here. That's what you should get out of this, right? Not that you have to calculate it using this horrendous definition here, very complicated and probably, it's very hard to understand. But if you can calculate this area, then that's the value of this integral, right? And so we can actually do this for some very simple regions, right? So for example, yeah. All right, so let's find, how about the definite integral? Let's go from 0 to 3 of x plus 2 dx, right? So in this case, my f of x is just x plus 2. Oops. X plus 2. Right. And so we want to calculate what this number is, right? Well, it's an area, right? It's an area of what? Well, let's draw it out here. So let's draw this specific graph. Okay, it might be a little sloppy, but I think you'll get the idea. 1, 2, 3. Okay, so y equals x plus 2. What's that going to look like? It's just going to be this straight line here has y-intercept 2, right? And it keeps going. So this is just my function f of x. It's a linear function, x plus 2, right? And now we're going from x equals 0 to x equals 3. So here's, can I use red again here? So here's 0, and then here's 3, right? And so, yeah, we want the area above the x-axis, right? But below this line here. Okay, so that shaded area in there. And maybe I shouldn't have shaded it in because, well, yeah, I can fill it in later. Well, here, let me just do that, right? It's this area here. That was easy. Okay. So how do we calculate that area? Well, if you're clever about it, you notice that you can divide this into two parts, right? Right here, and maybe I should, let's see if I can give this a slightly different color. Yeah, so that'll be purple, and then the top part will be red. Okay. So let's start with the purple area here. What does that look like? Well, it's a rectangle, right? So 0, 1, 2, 3. So the length of the rectangle is just 3. And what's the height? Well, notice that over here, this is when x is 0. When x is 0, f of x is, well, 0 plus 2, right? It's just 2. So the height is 2, right? So the purple region here, the area of that rectangle is just 3 times 2, right? 3 times 2, which is 6, right? Yeah. So, right. So that's just the purple rectangle. What about the red area? Well, that's definitely a triangle, right? Again, the length, the base of the triangle is still 3. What's the height from here to here? So what's the y-coordinate here? So, well, the way I drew it, it looks like 4, but it should be 5, right? It's just 3 plus 2. So when x is 3, y is 5, right? But this is 2, so you're going from 2 to 5, so the height is 3. So if the length is 3 and the height is 3, remember for a triangle, let's squeeze that in here, you have 1/2 the base times the height. Well, if the base is 3 and the height is 3, that's going to be 9 divided by 2, right? Or 4.5. Right. So that's going to be, yeah, I'll write it again here, 1/2 3 times 3, which is just 9 over 2. So what do you get when you add 6 plus 9 over 2. You get 12 over 2 plus 9 over 2, 21 over 2. Right? So that's the total area of the triangle plus the rectangle. Right? The red triangle plus the purple rectangle. Right? And it's also just 10.5 if you prefer decimals. Right? But that's it, right? That's going to be the value of this definite integral from 0 to 3 of x plus 2 dx, right? That answer there is 10.5 or 21 over 2. Okay? Right, and so, yeah, we didn't have to do any Riemann sums. We didn't have to calculate any limits here. We just had to know how to find the area of a rectangle and a triangle. And I think you can handle that. That's just basic geometry here. Okay. Right. Now, obviously, that's because this is a very simple curve. In fact, it's not a curve. It's a straight line, right? But yes, if you had a function more complicated, right, maybe one that looks like this, right, then finding the area is not so easy, right? And in fact, the idea is we're going to find a way to calculate these types of integrals in general in the next, in the next section, right, in section 4.4. And then we're going to work backwards and say, well, now that I know how to calculate that integral, now I know what the area is, right? Now I know what this area is. Yeah, that's the area here, right? So, right, so that's what we're going to do. But here, we calculated the area, because it's just a rectangle and triangle. We know how to do that. And so that's how we calculated this definite integral. Make sense? Okay. So now, remember, we want to talk about properties. Let's get to the properties. And here they are. So these are theorems that we could prove, but we're not. We're just going to state them and kind of take them at face value. So the first theorem, theorem 4.4, says that in continuity implies integrability. So to translate that, theorem for 4.4, right, all continuous functions are integrable. Right. So what that means is, if you have a continuous function, you can always find the area, right? The area will exist and it'll be finite, right? So when you have a continuous function on a closed interval, that's actually important. It has to be closed. Open intervals, then all bets are off. It might not be integrable, right? Integrable just means you have a finite area, right? That limit exists, right? Yeah. So yes, so any continuous function on a closed interval, right, on a closed and bounded interval, you can always find the area, right? And that just makes sense, right? Even if you have a function that has like a gap in it, like this, right? Or if it has a kink like this, it might not be differentiable. But let's say we're going from here to here. You can divide this up into this part, find that area, and then find this area, and rest assured that it's just some number, right? It will exist if you're going from A to B. Okay, so yeah, all continuous functions are automatically integrable. And by extension, that means all differentiable functions are also integrable. So remember, differentiable is more strict. It means you can't have this corner here. So yes, so continuous functions are integrable, differentiable most functions that you and I deal with, on a daily basis, well, as mathematicians and scientists, are going to be integrable. But there are functions that are not integrable, and well, that can happen for a number of reasons. One might be something like this. Let's say your function looks like this. Right? So you might have a vertical asymptote. Well, remember, the definite integral is the area in here, and this area in here, because it goes up forever, even though it's tiny up here, because it goes on forever, it might not be finite, right? So yes, right? So that's one thing that can happen. Of course, another thing is that if it's not a closed interval, if you want to go on forever, like let's say you have just a straight line, but we're going from, let's say, 0 to infinity, well, obviously, as the further out to the right you go, your area is just going to get bigger and bigger and bigger, which means it's not finite, right? So in that case, it would not be integrable in that sense, right? Okay. So, yes. So the definition, right, f is integrable on a closed interval. Oh, I'm sorry. Yeah, so we already talked about that, right? So this is another definition. I'm sorry. So suppose we have a function that is integrable, right? And that means, right, it might not be continuous or differentiable, but it's even better. It's integrable, right? So it has a finite area, not like these. Then what we can say, if we take the definite integral from a to a, right, you just get 0. So if you take the definite integral from a to a of any integrable function, you have to get 0. Right? So what would that mean? Well, let's say this is my a right here. When you're going from a to a, oops, let's try that again. If you're going from a to a, there's no rectangle, right? The width is 0. Your delta x here is 0. So you have a height, right? Your height is just f of a, but there's no width. So the total area is 0. Right? So that just makes sense. Okay. The other property here, also, this is one we're going to actually use quite a lot. Let's suppose instead of from a to b, you want to go from b to a. Right? So in fact, let's draw that out. Let's say this is a, this is b. For the moment, we're always assuming that a is less than b, although it doesn't have to be. Sorry, that's my b there. Okay, right, and then you have your continuous function or your integrable function, right? And you want to calculate the area from a to b. Sorry, a to b here. Right, but what happens if you go from a to b? I'm sorry, from b to a. In other words, you're going backwards. You're going right to left. Well, right, left to right is positive, right? Right to left is negative. So even though this area will be finite, when you calculate the definite integral from a to b, you don't get the same thing. You get the opposite, right? You get a negative sign in front. So yes, when you switch the upper and lower bounds, right, the upper and lower limits of the integral, you get a minus sign, right? So without having to do any work here, if you want to calculate, let's say, the definite integral from 7 to 3 of some function, let's say x cubed, right? Well, if you want to go from 3 to 7 of the same function, you don't get the same thing. You get the opposite, right? You always get that minus sign. That's what the definition up here says, right? Way up here on the right. Okay, so again, that makes sense because instead of going right to left, you're going left to right, you're going right to left. You're going in the opposite direction, so that gives you the opposite sign, the negative sign. So I hope that helps. Okay. Yep, one more, Theorem 4.6, right? So this is the additive interval property, right? And it just says that if you have an integrable function, remember integral just means that it's finite area, basically, on a closed and bounded interval. And if you divide that interval up into just, from at some point c in the middle here, that you can do this, right? You can take the integral from a to b and just go from a to c and then from c to b. Okay, so let's go down here and I'll show you what that means. So let's say we have our interval from a to b, and we have some integrable function. Right, let's say it looks like this. Right. So that's my f of x. And so we want to calculate the integral from a to b. right, which will just be the area in here, right, in this region here. I'll call this region R, right? Well, I mean, you know, at this point we can do that. Or let's say we divide this up, well, let's say right here, right? So this will be my C, right? It doesn't have to be at the minimum here, but it, you know, it might be, it could be, right? So if I calculate this area in here, and that's going to be the area from A to C of the, oops, sorry, that's a C. Right, here's C of the same function, right? So that's this green area in here, right? And then let's say I calculate this area in here, right, the whole thing, right? Here we're going from C to B, right? So that's going to be the definite integral from C to B of the same function. That's f of x, right? Well, what happens when you add up, right, the area, the green area plus the orange area? You get the full area, right? You get the area going from all the way from A to B, right? Areas just add. When you add the areas, you get the total area, right? So that's all this says, right? That's all this property says, is that if you want, you can divide up your interval into two or more, right? You can add a D here. Then you're going from A to C, C to D, and then D to B, right? So you would have three of these here, right? A to C of your f dx plus C to D, f dx plus D to B, f dx. I hope you can read that. And of course, that'll just be the same thing as going all the way from A to B. Okay. So yes, this is the additive interval property, right? You're just adding up the areas of each piece of it. Okay, so right, so that's some properties. We got to do, I think, a couple more, and then that'll be it for this section. Okay, so two more properties. This is Theorem 4.7, and it might look a little familiar, right? It's the constant times function rule and the sum rule. So the first part, and I'm pretty much just going to copy it down here so it's maybe a little more clear if you can't read this. Right, so the first part just says that if I have the definite integral from A to B of some constant k times the function, right, that I can just calculate the definite integral of the function itself and then multiply that whole number times k. In other words, right, the constant can come outside. Right? And we already saw that with indefinite integrals, so maybe it's not surprising that it works for definite integrals as well. Just keep in mind that indefinite integrals are functions plus a constant, and definite integrals are just numbers. Right? So here you're just multiplying k times this number, and you get this other number here. Right? Of course, you also have the sum rule, right? So if you have two functions, say f of x plus g of x, and you want to add them, right? F plus g, you get another function. What's that definite integral? So maybe not surprising that you can go from A to B of the function f, right? So find that area, and then add the area under g. So this is the sum rule, right? It's the sum rule for indefinite integrals, but it also works for definite integrals as well, right? And of course, it works as a difference rule as well. For example, if this k here were -1, then you can apply the sum rule and the constant function rule and just subtract, right? So it also works if you're subtracting. So it's the sum or difference rule. Right, so yes, it works for indefinite integrals from 4.1, and it works for definite integrals in 4.2 and 3. Yeah, oh, well, sure. So before going on, we might want to say, suppose I have the definite integral from A to B of f of x times g of x. Right, So we're looking for a product rule. And if you remember, in 4.2, or 4.1 rather, for indefinite integrals, we said there is no product rule. And likewise, for definite integrals, there's no product rule, right? This is not going to be the definite integral from a to b of f times the definite integral from a to b of g. Okay, it just doesn't work that way. You're not going to be able to do that. So don't even try. It just doesn't work, right? I mean, in some sense, yes, areas don't multiply, right? If you have the area of under two different functions, you don't multiply the areas, right? You can add them or subtract them, but you can't multiply or divide, right? So there's no product rule, right? No quotient rule. And even though that doesn't make sense here, there's no chain rule either, right? No chain rule. In other words, there's no rule that says what to do when you have, say, f of g of x, right? How do I calculate that in terms of f and g? Well, you know, we'll get to ways maybe around this, right? But there's no rule for it, right? There might be techniques, but there's no rule that says, oh yeah, if I see this, I can do this, right? You can only do that for a constant times a function and a sum or difference, and that's it. Those are really the only rules we have, right, for definite integrals and for indefinite integrals as well. All right, the next thing is you have an integrable function, right? And if it's non-negative, and in terms of the graph, that just means that, well, so I'll go over here now. So here's my x-axis, here's my y-axis. If I have a non-negative function, that means it can't go below the x-axis, right? Because here y would be negative. So it would have to be, right, either 0, so it can just touch the x-axis, or go above it, but not below, right? So if that's my a to b, right, then the definite integral, remember, is just this area in here, right? This area plus this area. Oops. Right, and so that total area, well, it has to be positive, right? It's either greater than 0 or equal to 0. Right? So that just makes sense, right? For any function above the x-axis, your area is positive. So what happens if it goes below the x-axis, right? If it does this, then this definite integral would count this as negative, right? We don't want to say the area is negative, but the definite integral would count that as a negative region, right? Because y is negative, you can think of the height of the rectangles as being negative. And so because of that, this might not hold, right? So yes, this has to be non-negative in order for that to work. Okay. And then number 2, if you have two functions that are integrable and f is always less than g, then the definite integrals have to follow that same inequality. The definite integral of f has to be less than the definite integral of g. Right. And so I'm going to explain that with a picture as well, but I got to go down here to do it. So, all right, so we have some graph, and I'll just call it f of x. Right, so it looks like that. And then remember, g of x has to be bigger than f of x. So my g of x might look like this, although it could be equal, right? So they could touch somewhere, but they can't cross. They can't do that. Okay, so I'm not going to even have them touch. I'm going to say g of x is always going to be bigger than f of x. Okay, so let's just go from a to b. So here's my a, here's my b. So what would the definite integral from a to b of f of x be? Well, it would be this purple area in here, and I don't have the area yet, so I'm going to highlight it. Yep, it's this area in here. Oh, sorry. Sorry about that. Yeah, it's this area in here is this definite integral here. Make sense? Okay. Now, let's do the definite integral from a to b of g of x. What would that be? Well, that's also going to be an area, and it's going to be this area in here, right? In fact, let's highlight it all. Yep, it's going to be this, right? However, right, it's everywhere above the x-axis, right? In other words, it also includes the purple area in here as well. So it's the whole thing, right? So all we're saying here is that if you take, oops, I don't want to do that again. If you take the definite integral from a to b of f of x, then it has to be less than or equal to the definite integral of g of x, right? Because, in other words, the green area here has to be bigger than the purple area. Oh, I'm afraid of doing that, right? Oh, shoot. I think I messed this up, so yeah. Well, you remember the purple area, right? It was here, down here. Oh, yeah, that was what I was afraid of, right? Okay. Yeah, so I'll have to do this, right? Let's divide this up again. So here was the original function, f of x. And I think now I can highlight the purple area, right? So yeah, the green area here is bigger than the purple area. Right. Great. So that's all this said. Oops. I knew I was going to do that again. Here we go. That's all that this inequality says. Right. And so that was theorem 4.8 part 2. Right. It's this inequality here. And I just rewrote it down here. All right. So that's it. That's all we need from section 4.3. And so maybe we should do some examples. Yep, let's do that down here. All right. So example 1. Okay, so we are given these definite integrals here, right? So we're given all of this up here. And using the properties that we know, we want to evaluate these definite integrals. Okay. So let's start with the first one. Part A, we want to take the definite integral from 2 to 10 of f of x. So notice that the first one here goes from 2 to 7, and the second one goes from 7 to 10. Well, if you're going from, maybe I shouldn't do that. If you're going from 2 to 7, you're getting part of the way there, right? And then you want to go from 7 to 10. And if you go from 2 to 7, then 7 to 10, you're going all the way from 2 to 10, right? So this is that additive interval property, right? So we know what the first integral is. That was given. That was 15. And then the second one is 9. So 15 plus 9 is 24. And that's the answer. Right? So that's all there is. Even not knowing anything about what this f of x is. We don't know whether f of x is, x squared or sine of x. We have no idea. But it doesn't matter, right? Because whatever that function is, it has a definite integral, and based on the ones that were given, we can evaluate these definite integrals here, right? Right, so how about part B? We're going from 7 to 10 of negative 4 times f of x. Okay. Well, we know 7 to 10, right? That's 7 to 10 here, right, of f of x. We know that that's 9, right? But what about this negative 4? Well, it's a constant, right? Remember, constants can come in front. So this is just negative 4 times the definite integral from 7 to 10 of f of x, right? And then this integral here is, of course, the same as this. So we know it's equal to 9, right? So it's just negative 4 times 9, right? Which is negative 36. Now remember, definite integrals can be positive or negative. right? We're not saying the area is a negative number, but, right, this area, the 9, is positive. When you multiply any positive number times a negative number, like -4, of course you just get a negative. So definite integrals can be negative, even though areas are not. Okay, so keep that in mind. All right, what about part C here? So for part C, we're going from 2 to 10, right, of f of x plus g of x. Well, that looks like the sum rule, right? It looks like we can split this up, going from 2 to 10 of f of x plus the integral from 2 to 10 of g of x, right? So you're just using, this is by the sum rule, allows you to do that. Oh, don't forget the dx, right? The dx is important there, right? So what's the first integral? Well, we calculated that already. In part A, that was just 24. So the first term here is just 24. And what about this definite integral here? Well, that was given. That was given up here. That's 6, right? So 24 plus 6 is 30. So just using the sum rule, that's what you get, right? All right. And finally, part D here, we have the definite integral from 7 to 2. Now that looks backwards, right? Because we are given the integral from 2 to 7. And generally speaking, this lower number here should be smaller than this upper number. But in this case, the lower number is bigger than the upper number. And that should not happen, right? But it can. It does here. And so how do we switch them? How do we go from 7 to 2 to 2 to 7? Well, you're allowed to switch them as long as you don't forget there's a minus sign in front, right? So that negative sign will switch the upper and lower limits here from 7 to 2 to 2 to 7. And we know what happens from 2 to 7. That's just 15. But now there's a negative in front, so now it's negative 15. Okay. So, right, so I hope that helps, just using the properties that we just talked about. And I know I erased them, but you should get comfortable enough to use them without having to look at them, without having to look them up. So that's kind of what I did here, right? So I want to do one more. This is a tricky one. We're going from 2 to 7, and let me maybe bring it up a little bit higher so we can see it. Okay, so I think I cut off the values here. Oh, this was way before. Oh, I did keep some of the properties that I used down here, but not all of them. All right, so this is the definite integral from 2 to 7 of 3 plus f of x dx. Okay, well, we do have the sum rule, right? Same rule that we used in part C up here, we can use again in part E. Right? Now in this case, the first summand, right, is just 3, so that's my f of x, and my f of x is now g of x. But, you can just go from 2 to 7 of 3 dx plus the definite integral from 2 to 7 of f dx. Okay, and let's do the second one first because we know that one, right? That's just equal to, well, that was given way up here. That was 15, right? So that's going to be plus 15. Yep, plus 15. And now we have to look at the first one here, right? So this one here is going to be a little tricky. What's the definite integral from 2 to 7 of 3 dx? So none of the properties that we really talked about here is going to help us. So now to do this, we're just going to have to go back and think about what this means. Okay, so let's draw the graph, right? Let's draw the graph, right? So 1, 2, 3, 4, 5, 6, 7. So here's 7, here's 2. And then 1, 2, 3, 4, 5. It doesn't matter. So here's 3. Y equals 3. You should recognize y equals 3 as a horizontal line. That's close enough, right? Oh, yeah, it keeps going, of course, both left and right. But we're only going from 2 to 7. So we're starting here at 2 and we're ending at 7. So what does this definite integral represent? It represents the area of this region. Under the curve, in this case a horizontal line, right? But above the x-axis and between 2 and 7. Well, that's a rectangle, and I hope you can recognize, right, that the length of the rectangle is just 7 minus 2, which is 5. And the height of the rectangle is just, well, this goes from 0 to 3. So 3, right? So length times width, or I should say length times height, is 5 times 3, right? So that's also 15. So this first one here is also 15. So yeah, 15 plus 15 is 30. And that's the answer, right? So yeah, you have to be careful. You don't just add 3 plus 15, right? This 3 is the height of your rectangle, right? The length goes from 2 to 7. So 7 minus 2 is 5, right? From here to here is 5 units. So 5 times 3, that's what gives you the 15 here, right? And just to be clear, they're both 15, but, right, so, oops. I meant to do that in a different color here. Yep. So this integral here is this 15 here. When you add them, you get 30, which is the value. So I hope that helps, right? So that this is a pretty reasonable example using the properties up here and then the ones that I had before that in order to calculate these definite integrals when, of course, you have to be given these integrals up here, right? So yeah, without these, we wouldn't get very far, right? So so I think that's basically it for 4.3. There's maybe a couple other types of questions, but that's this is most of it, I think. So just make sure you know the properties, or at least be able to look them up very quickly, but ideally you should get used to them, these properties up here, and then the ones we had before. So, all right, so that's it for 4.3. I hope this helps a little bit.